Good morning, Vivek sir and Animesh sir. Today our group will be presenting our major project and we have done data analytics using Spark MLlib and what we have used is linear regression. So to start, I'll give a small introduction on what Apache Spark is. So Apache Spark is basically an open source distributed processing system used for processing data. It utilizes in-memory caching and optimized query execution for fast analytic queries against any data. It provides development APIs in Python, Scala, R, and Java, and it supports code reuse. So we could code and work with Spark using these four languages. Next slide. Now, why are we using Spark? Spark has a few advantages. One, that it's fast, it uses in-memory caching, and it's developer friendly. We had mentioned the four languages, the APIs we can use, and it has multiple workloads, which we'll see in the next slide. And it has ease of use. It has easy APIs and easy to work with. Next slide. These are the Apache Spark workloads, which was mentioned earlier. There are four workloads, which is MLlib, which we have used for the project machine learning. There is streaming, which is real-time analytics, SQL, interactive queries, and graphics for graph processing. All these four workloads can be worked on with the same four languages. Next slide. Now, the machine learning algorithms, these are a few algorithms that are provided in the Spark MLlib library, which is classification, regression, clustering, reinforcement learning, association rules. We have used regression over here for our project. Now, next, first, what we did was we basically downloaded Spark in order to work with it. For that, we have to download it from its official website and then store it in a folder in the particular location. And then what we have to do is configure the environment and path variables. Next slide. So in the path variables, we gave the specific location, the path, that folder in which we downloaded, and we gave the variable name as Spark Home. Next. Yeah, these are just screenshots of how we access the environment variables and whatnot. Next. As you can see, we set the variables for the language as well. Next. Yes, over here we have set the value.
So I will be explaining about linear regression. So as Rehan had told that it is part of Spark's ML library. So linear regression is a supervised learning machine learning algorithm, and it defines the relationship between an independent variable and a dependent variable. So the independent variable is the variable which needs to be given inputs on which the dependent variable will make predictions. And the general formula for linear regression is y equal to a naught plus a1 into x, where a naught is the intercept and a1 is the slope. So previously we had implemented linear regression by using a small data set, that is a student grades data set. So as you can see on the graph, we can see on y-axis there is student grades, and on x-axis there is time to study. So each data point represents the number of hours a student studied to get a corresponding grade. So in terms of simple linear regression, the formula becomes grades equal to a naught plus a1 into time to study. So now we have implemented multiple linear regression, and we have used another data set, that is an e-commerce website data set, which uses customers information, and it predicts the yearly amount spent by the customer. So in this, how is it different from simple linear regression is that instead of one independent variable, we're using multiple independent variables. So in turn, our formula becomes yearly amount spent is equal to A0 plus A1 into average session length plus A2 into time on the app plus A3 into time on the website plus A4 into length of the membership. So these four are the extra independent variables that we have used. So as you can see from the graph, there are many lines. So how do we find which line is the best fit line? So in order to find the best fit line, as you can see, there are many data points. So we take one line and then we take one data point and name it as yi, and we project this data point on the line and we name it as yi cap, and then using the least squares method, we sum all the data points and we find a minimum value. This is called sum of squares of residual. So as you can see, like these two from our human eyes, we can see that these two are not best fit lines. But it becomes difficult to find which is the best fit line, as we have to draw many lines and we have to do trial and error. So we draw this to make it more simple. We draw this average line and we use the similar method and we take one data point and we name it as yj and project it on this average line and we name that point as yj hat, and we use the least squares method and we sum all the data points to get the sum of squares of total. So why do we use these two, SS residual and SS total? So we define a method called R square to find the relationship between SS residual and SS total. So as we find the minimum value of SS residual, the SS residual by SS total becomes a minimum value, and in turn the whole equation, that is the R square equation, becomes closer to 1. So if the R square value is closer to 1 or is equal to 1, then the model accuracy will be very good. But if the R square value is closer to 0, then the model accuracy is bad. So we can use the R square method only for until we find the simple linear regression. But when it comes to multiple linear regression, there are many independent variables added. So the SS residual, even if we add good independent variables or bad independent variables, the SS residual value will always be minimum. So we can't make the difference, like the R square value will always be higher. It will never decrease. So to rectify this problem, we introduce the adjusted R square. So here the formula is 1 minus R square into n minus 1 by n minus p minus 1, where p is the number of independent variables and n are the number of observations. So as we add some bad independent variable, the value will decrease. But if the R square value is high, it will be the whole adjusted R square value will show more, like it will show higher accuracy. But if the R square value is low, when we add bad independent variables, then the adjusted R square value will decrease. So that is how we can know the accuracy of multiple linear regression. So there are few more model evaluation techniques which will be explained by Safwan.
A very good morning. Hope I am audible. So here I will be explaining about some of the metrics which we have used to improve our ML model. So the first one is mean square error. Mean square error measures the average of the squares of the error, that is average square difference between the estimated values and the actual values. As we can see in the equation, the yi is the actual observation and the yi cap is the estimated values. So MSE is a risk function corresponding to the expected value of the squared error loss. MSE is a strictly positive value that decreases as the error approaches 0, and it is the most simple and common metric used for evaluating regression family of algorithms. Also, if we get the higher value of MSE, that depicts our model is not at all good, since there is a lot of error. To get a perfect model, the MSE value must be 0, or which must be approximately equal to 0. Next slide. So root mean square error, the RMSE represent the square root of the second sample moment of the difference between predicted values and the observed values. This deviation is also called as residuals. This basically tells us how concentrated the data is around the best fit line. And this metric is introduced to bring errors on the same scale as that of the targeted values. Also, RMSE is the square root of the average of squared errors. The effect of each error on RMSE is proportional to the size of the squared error. Thus, larger errors have a disproportionately large effect on RMSE. Next slide. So here we have mean absolute error. In this metric, we calculate the error as the average of absolute difference between the calculate and observed values. The MAE and RMSE can be used together to diagnose the variation in the errors in a set of forecasts. The RMSE will always be larger or equal to the MAE, and the greater the difference between them, the greater the variance in the individual errors in the sample observation. Also, if the RMSE is equal to MAE, then all the errors are of same magnitude, and both can range from the value 0 to infinity. Next slide, please. So from here onwards, we will be discussing about the parallel processing of Spark. So we know that Apache Spark breaks our application into many smaller tasks and assign them to executors. So Spark executes the operations in parallel. Spark splits data into partitions and execute computation on the partitions in parallel. Each partition is a CSV file where you write a data frame to a disk. Parallel processing is possible in both local mode and cluster mode. What Spark actually does is simply it reads some data, load it into Spark, then process it, hold intermediate results, and finally it will write the results back to the destinations. But this process needs a data structure to hold the data. And here in Spark, we have three alternatives to hold the data. The first one is data frame, then data set, then RDD. And Apache Spark recommends to use the data frame and data set to store the data, as to input the data, and to avoid RDD. But ultimately, data frame and data sets are compiled down to RDD itself. So everything in Spark is a RDD. Next slide. So in this, we will discuss about the importance of RDD. Data in RDD is split into chunks based on key. RDDs are highly resilient, that is, they are able to recover quickly from any issues. As the same data chunks are replicated across multiple executor nodes, so if one executor fails, another will still process and find the success, which allowing functional calculations against our data are very quickly possible. And from this, we can reach a conclusion that RDD is a layer of abstracted data over the distributed collection. It is immutable in nature and follow lazy transformations. And immutable means an object whose state cannot be modified after it is created, but can surely be transformed. Next slide. And this is the workflow of an RDD. So when we create a RDD, or the data input we have done, which can be further be automatically create RDD, it will be further undergo some transformations, and it will split into many RDDs, and which will eventually gives the results. So talking about the distribution environment, each data set in RDD is divided into logical partitions, which may be computed on different nodes of the cluster. Due to this, we can perform transformations or actions on the complete data parallelly. Next slide. So here we'll be discussing the parallel processing execution sequence in Spark. Uh, RDD is usually created from external data sources like local files or HDFs. RDD undergoes a series of parallel transformations like filter, map, group by, and join, where each transformation provides a different RDD, which gets fed to the next transformation. The last stage is of action where RDD is exported as an output to external data source. Next slide. So this is the internal mechanism what Spark is having. That is the architecture of Spark. So there is a driver program within the Spark cluster where the application logic execution is stored. Here the data is stored in parallel with multiple workers inside driver program. First thing we do is create a Spark context. Spark context is the gateway to all Spark functionalities. Now the Spark context works with the cluster manager to manage various jobs. A job is split into multiple tasks which are distributed over the worker nodes. And among workers, data is placed side by side and partitioned within the cluster across the same machine. The driver program during execution passes the code into worker machine where processing will be conducted of the corresponding partition of data. And with the increase in number of workers, memory size will also increase and we can cache the jobs to execute it faster. To prevent data shuffling, data will undergo different steps of transformations. And finally, at the worker nodes, actions are executed and the result is returned to the driver program itself. Next slide. So here we'll see parallelization with respect to Spark architecture. Since Spark is a distributed environment, we store vectors row by row. In each row, we have the features, weights, and responses. The row-wise data is partitioned. Like the partition data can have number of features. About the partition will be based on default. It will be based on the number of the cores of our machine, and we can program it accordingly, the example of which will be shown in the upcoming slides. Next slide, please. So here we will see the what will happen for logistic regression or linear regression. Linear regression follows the same pattern as logistic regression. So what will happen in with respect to the Spark architecture, what is going to happen inside each nodes and all we will see. So in each iteration, we start with broadcasting the coefficients into executors, where it compute the loss and gradient in parallel in all the executors. And then we will reduce them to loss sum and gradient sum in drivers. The aggregate of the gradients and loss scales linearly with respect to the number of executors. And in the driver, we will execute the optimization algorithms. Like in this problem, we have chosen LBFGS. So at finally, we will give the coefficients back, and this is an iterative process which will continue. Next slide. So here we'll see if the data is very high, it can be split into a number of executors, but the data coming out from executors to driver, so it will make a huge load for the driver. So here we'll see how to reduce the load of the driver. So multi-level aggregation step used in improved versions of Spark, like the newer versions of Spark is following this architecture. This will reduce the load of the driver. This type of methods can reduce the aggregation time by the order of magnitude. Like in the driver, the reduced in data which have taken from the executors will again have a parallel execution. Like here we can see 4 executors are there. The data coming from executors is taken for reducing the aggregation process, and which is which is in 2 and which is further reduced to one aggregation process. Likewise, the load is reduced in the driver itself. Next slide. From here, the example of partition will be explained by Initial.
So as you can see in the command line, we have run Spark shell as master local 2. That means we are running it in 2 cores. So when we read a file, when you give the command to read a file, and if we want to know how many partitions are being made, we run the command get some partitions, and the output is 2 cores. So if we add 4 cores or 8 cores, the output will be 4 or 8 respectively. So in the linear regression function, the objective function will be calculated. So the objective function is a sum of 2 parts. That is the regularizer that controls the complexity of the model, and it prevents overfitting. And the other part is the loss function that measures the errors of the model. So there are many types of loss functions and regularizers. So some of the regularizers are L1, L2, and elastic net, which is a combination of L1 and L2. And some of the loss functions are hinge loss, squared loss, etc. So we are using squared loss. So when we use squared loss, the regularizer will be chosen as none, and we pass this as parameters to the linear regression function, and we pass the independent variable, and then the objective function will be calculated, which will decide the best fit, which will decide the best fit line. After calculating the optimization function, the objective function, we choose optimization method internally, and some methods which Spark supports are SGD and LBFGS. So based on the methods we have chosen, they have different convergence guarantees and different properties based on the objective function. So in general, LBFGS is recommended since it calculates it optimizes the objective functions and converges faster in fewer iterations than SGD. So Vivek will be explaining the data set used and the code of that program.
So this is the data set where we perform the simple linear regression in our midsum to predict the grade of a student with respect to the time it took. So now we have done the multiple linear regression. So this is the data set we have used. So this is an e-commerce website data set, which includes these columns like email address, time on app, time on website, yearly amount spent, and length of membership. So we will perform multiple linear regression on this data set to predict the yearly amount spent by a customer. Yeah, so first for that we'll configure the PySpark, and you are starting the Spark session here. That's what we have done in first two course here. And then Spark is equal to Spark session dot builder dot app name. So first what we are doing is we are initializing the Spark session and naming it as a Spark session dot builder dot app name, and this app name be like customers, and we are just creating it. So this is basically naming Spark session and creating it. And the next line, if you see dataset is equal to spark dot read dot csv e-commerce. Yeah, so here we are reading those dataset e-commerce dot customer dot csv, and we are giving the values for info schema and header as true. So info schema is basically this Spark session will automatically understand what kind of data type it is. So whether it is a string or double or integer, etc. And we have given header is equal to true just to display the header or the column of our data set. And in the next dataset dot sorry, previously one more code is there. Yeah. So here dataset dot print schema. So here we are is nothing. We are just printing the schema to take a look at what data types info schema equals to true has said for our data set. So if you see here as the output, we have whatever we are given, like for email string and address will in string data type, time on app on double data type, and time on website on double data type. Yes. So yeah, data set dot show. So this is what we have done till now, that our entire data set we have been included. And the next one is data set dot head function. Yeah, this is just to see the display whatever we have did now in our first column. So if you see here, whatever we have did for email, we have given the string, and it is in a yeah, M Stevenson at Fernandez.com, and like that for average session length in a double data type. Yeah, so everything is in proper way. So now next going to the from PYSPARK.ml.linear import vectors. So first of all, uh, the first thing we need to do on setting up machine learning algorithms, particularly when we are using PySpark, is to get things in a proper setup. So we'll take this PySpark.ml.linear algebra and imports this vectors and vector assembler. So this vector assembler is nothing but it's a collection of all the vectors. And the next slide, sorry, in the next one, data set dot columns. Yeah, next slide, please. Yeah, data set dot columns is nothing. Just we are just displaying the columns for our next step. That the next step is assembler is equal to vector assembler input column. Yeah, so here we are creating our assembler and vector assembler and input column. So input column is nothing but all my independent features. So I need those all that independent features to get, so that I've given the code before. I just want to take which part as the independent features. So I have taken the first one as average session length and time on app, time on website, and length of the membership. And then I've created output code is equal to feature. So I just created one more column, like output column. So I'm going to define my output column and specify by name like feature. And if you see output is equal to assembler dot transform dataset. So is and just creating the variable output and transformed data, and we are getting the transformed value that is in features in an array form. So if you see in the next code, output dot select features dot show, yeah, you can see the features column that we have just created. Yeah, next slide, please. Next slide, you can see it. Yeah, so in next, we need this independent features and dependent features, that is the label to perform our method. So final data is equal to output dot select features and yearly amount spent. So we have taken the features as our independent and yearly amount spent as our dependent feature, that is our label. And you can see the next train data, test data, final data to random split 0.7, 0.3. So here we are using this. Actually, we are training this into our train data and test data, which means we are using this random split method in order to define the ratio as 0.7 and 0.3, which means we are splitting the data like trained data is having 70% of the observation and test data having 30% of the observation. So yeah, so here we are trying to analyze the test and train data using the dot describe function. And the next one, we are importing this linear regression part. So here we are modeling it like from PySpark ML regression import linear regression, and LR is equal to linear regression label column is equal to yearly amount spent. So here we are modeling it and initializing the model LR. So this LR is going to be our linear regression model, and the label will be yearly amount spent. And then next slide, please. And yeah, we are just creating our model, and so we are going to fit this in our training data. So for that, we need to find out the coefficient and the intercept value. So for finding those, we are using this model dot coefficient and model dot intercept to find the coefficient and intercept respectively. So here, as you know, like for multiple linear regression, multiple independent variables will be there. So for that each variable we need to find the coefficient. So here for the indexes, average session length, time on app, time on website, and length of the membership, we have found the coefficients here. If you see in the output here, so here if there is 1 unit increase in our average session length, for example, 1 minute increase, then there is going to be a $25 of our yearly income. So same on this time on app, for any minute or hour which is added on adds $38. So then similarly on time on website and length of the membership. And the next code intercept is equal to model dot, yeah, as I told before, we are finding the intercept using model dot intercept method, and we have got the value as minus 1.1044.66 here. And the next is res is equal to model dot evaluate test data. So here we are evaluating our model by passing the prediction. So for that we have to add the predictions here. So we created an unlabeled data and by selecting the features, that is unlabeled data is equal to test data select features, and now we need to check the accuracy of the model. So we created the predictions, and we want to do our model, that is model dot transform. So if you see res dot prediction show function here, the next slide please. Yeah, so this is the predictions we have got and the actual data, the yearly amount spent. If you see this both means, we can say like it's almost similar, like 266 and 285, 467 and 471, 490, 493. So you can say till now what have we done is actually pretty good. So now we need to find out how good our model was. So we need to evaluate our model using different regression model evaluation matrices, my friend. Safan told mean absolute error, root mean square, mean square error, R square, and adjacent R square. And yes, in this slide. And yes, we got the values here. So if you see here as the output, um, it's actually pretty good. We are looking at about 98% of the accuracy. As my friend Nishi told, like if it is closer to one, our model is pretty good, and plus or minus $10 for our root mean score, which is also good. So we can say that our model is perfect model to find and the yearly amount spent by a customer. Yes, thank you, sir.
Nice presentation.